Okay, so welcome to lecture once again, guys. Now, in this lecture, I will be talking about a vector database, and I'll be talking about a working mechanism of a vector database, how it is going to store the data, how it is going to perform the indexing operation on top of the data, how it is going to perform a similarity search, or you can say cosine similarity, equivalent distance kind of a things on top of the data set. This part is pretty much important because whenever you are going to build any kind of a system which requires a vector database, for example, a RAG application, if you are going to build, obviously you are going to encounter such things, and obviously you will have to deal with it, and you must be having an idea about the mathematical execution behind the scene, and that is something which I am going to show you, that is something which I am going to explain you now in this particular lecture. So let's try to understand one by one, everything. So here we are going to talk about basically vector database. Yeah, we are going to talk about vector database. Now, what is a vector, by the way? So let's suppose if I am writing a 1 comma 2, so I am trying to say simply that, okay, so there is a entity, and that entity is having maybe 1 along an x-axis, right, magnitude wise, and then 2 along the y-axis. So maybe here this dot is going to represent this entire entity. So where I have x is equals to 1 and y is equals to 2, and this is going to be a vector, right? This is going to be a vector A, let's suppose. This is going to be a vector A. So an entity which is having a direction as well as which is having a dimension, it's called as vector, right? It's called as vector. Now, so whenever we talk about generative AI, or whenever we talk about like a RAG application, so over there you must have encountered that we are using a vector database, right? We are using a vector database. So what we are trying to achieve with the help of vector database? So we are trying to store our images, we are trying to store our text, we are trying to store our entire like a movie file maybe, or any kind of a data in a form of a vector, means in this particular format with maybe a very high dimension. So maybe with a 1236 or 1536 dimension or something like that, right? Or maybe 1000 plus dimension, maybe a 500 plus dimension, in which we are trying to store this data. Means we are converting eventually a data in a vector form. So whether we have a audio data, whether we have a image data, whether we have a textual information or any other information, so we are converting all of those information in a form of vector, and then we are trying to store it into a vector data. That's completely fine. We'll try to show you that part as well, that how we can try to store, how we can try to convert all such kind of a data in our upcoming lecture. But before that, we have to even understand that when we are trying to store all of this data, right, in a form of vector, how it is going to do a search operation, how it is going to perform like a, because at the end of the day, storing something into a vector DB simply means that it should help me out when I'm trying to search. It should give me a similar kind of a result, right? Then only we are going to use a vector DB. Otherwise, there is no use of like a vector DB. So how it is going to do a search operation, how it is going to perform the indexing operation, that is something which I am going to explain you in this particular lecture. So I'll just try to restrict myself towards these points. Yeah. So let's try to understand, and for that I would like to give you an example. I would like to take the example. So let's suppose we have some of the data set, right? So we have some of the data set over here. Now, what kind of a data set we have? So let's suppose we have a ID of the data, so ID 1, and then we have basically a vector, right? We have a vector. So I'm going to take a two-dimensional vector so that it will be easy for you to do a calculation and even to understand. Now you can extend it till any dimension, right? Or like till any length, that's completely fine. So ID is equals to 1. Let's suppose I have a vector 1 comma 2. Yeah. So ID is equals to 2. Let's suppose I have a vector 2 comma 3. ID is equals to 3, and let's suppose I have a vector 10 comma 10. ID is equals to 4, and I have vector 3 comma 2. Yeah. So let's suppose I am storing this information, this entire data set information into some of the database. Yeah, I am storing this entire information into some of the database. That's completely fine. I can try to store it. Then someone is trying to query, someone is trying to basically query with this particular vector. So with this particular vector 2 comma 2, someone is trying to query. Now whenever someone is trying to query with 2 comma 2, so obviously it should search inside this entire vector information which I am trying to store, right? It is supposed to search inside the entire vector information which I am trying to store over here, and it should always give me a similar data which is very much close or very much similar to the query or the question which I am trying to ask. Maybe this is my vector, right? This is my query. So it should always give me a data which is similar, right? Which is similar to this particular query from this entire vector set. So maybe it should give me like a top 2, top 1, top 3, top n, whatever it is, right? So, but it should give me information. Okay. Now, so how it is going to perform this query search operation inside the existing data set that you have? So first of all, what it does is that it is going to store this entire information, right? It is going to store this entire information by creating a indexes. So there is something called as IVF index. There is something called as what happened to my pen? Yeah. So there is something called as IVF index. It is going to create IVF index. Now, what is this IVF index, by the way? So IVF index, if I'm going to talk about a full form, so it's nothing but inverted file index. It's called as inverted file index. Now, how it is going to create this IVF index? So it's very simple. So based on the similarity, based on the clustering, so it is going to basically create the IVF indexes. It is going to keep a data together. For example, in this small data set, which is having just like a 4 example, right? So it is going to create a cluster. Let's suppose it is going to create a cluster, right? So cluster 1 it is going to create, and it is going to create a cluster 2, let's suppose. So in a 2 group, it is going to divide the data, for example. And why we are dividing it, I'll be talking about that as well. Yeah? I'll be talking about that as well. So here it is going to divide a data into 2 clusters. So it looks like that for ID number 1, ID number 2, ID number 4. So these data sets are like very, very close to each other. So maybe I can create a cluster 1, cluster 2 and cluster 3. So where data set is very much like, close to each other. And then I can try to create a cluster 2 where I can try to keep ID 3. So ID 1, ID 2, ID 3 comes inside the cluster 1, ID 2 and inside the cluster 2 we have basically ID. Sorry, I think I have done some mistake. So yeah, 1, 2 and 4. 1, 2 and 4 will come inside the cluster 1, as we can see that their data set is pretty much close to each other. And here, so inside ID 3, so I have 10 comma 10, so which is like a very much distant from all the other data sets. So maybe I can try to keep it here. So ID 3 will go inside a cluster number 2. So I'm trying to divide the original data. Why I'm dividing? I'll try to make a conclusion at the end of this lecture. But yeah, so I have divided this data into 2 clusters. Now, so this is basically we can do it with the help of inverted file indexing. So we are just like dividing this data into 2 clusters. Now, so whenever someone is trying to do a query, 2 comma 2, right? So it will try to, right? It will try to look into a cluster. So which cluster's data is near? So whether a cluster number 1 data is near or cluster number 2 data is near. Yeah. So whether cluster number 1 data is near or 2 data is near. So obviously a cluster 1 data set is near to this particular query. Yeah, near to this particular query. So what it will do, it will not even go with the comparison of with cluster number 2 data. So whatever data is available inside the cluster number 2, it will not even go and do the comparison. What it will always perform, it will go ahead and will try to do a query with respect to a cluster number 1. Now, so here it will try to do a comparison with 1, it will try to do a comparison with the 2, it will try to do a comparison with the 4, but not with the 3. Now, by doing this one, right, by doing this indexing operation or by doing this indexing partition operation, you can say, so we are trying to make this entire operation faster. As you can see that we have 4 inputs, right? Or we have 4 things inside my database. We have 4 entities inside my database or 4 vectors inside my database. I am able to avoid at least one, right? At least one comparison. So I'm not going to do comparison with respect to cluster number 2. I'm going to do a comparison with respect to only cluster number 1 set of the data. So that is the advantage you will be able to get. And as your data set is going to grow, so obviously you are going to divide a data into a multiple cluster. So you are avoiding a lot of computational overhead over here. Okay, that's cool. So inside a cluster number 1, we have like ID number 1, 2, and 4. Okay, so inside a cluster number 1, we have ID number 1 data, ID number 2 data, and ID number 4 data. Technically, we have ID1. ID1 data set is nothing but 1, 2. So 1, 2. ID2 data set is nothing but 2, 3. So ID2 data set is nothing but 2, 3. And ID4 data set is nothing but 3, 2. Yeah. So 3, 2. So these are my data set. These are my 3 like a data set which is available inside my cluster number 1. Okay, cool. And I have a query, and the query says that it's 2, 2. So with this 2, 2, I have to make the comparison, and I have to find out the top similar result. Yeah, top similar result. So here I can try to use a cosine similarity, or I can try to use basically a Euclidean distance. First of all, I would like to show you with respect to a cosine similarity over here. Yeah, cosine similarity. So here for a if we are trying to calculate a cosine similarity, so cosine similarity is nothing but cosine similarity for between two vectors a comma b is nothing but a dot product of a and b divided by norm of a and b. Simple, right? So this is something that is going to like give you basically this cosine for any vector, any two vector, right? Now, why we are even calculating this cosine similarity? What is a meaning of this cosine similarity? Let's try to understand that. Yeah, let's try to understand that. So formula wise, this is the formula that is like a completely fine. So this is the formula that we have for the cosine similarity, where a and b, so in a numerator, so we are trying to perform the dot product of two vectors a and b, and then in a denominator, so we are trying to perform the Euclidean norms, or you can say a length of the vector a and length of the vector b. So we are just trying to like multiply length of the vector a and length of the vector b, so that the entire result will depends upon the angle between two vectors. Now here, so cosine similarity will always try to give you a data, or it is always going to give you output between what? So between -1 to -1 to +1. So in between this, it is going to give you the final output. Now, if output is closer towards or moving towards a +1, right, it simply means that perfectly similar. If it is closer to a 0, the result is closer to a 0, then you can say that vectors are orthogonal, means there is a 90-degree between two vectors. And you can say that no similarity. And if it is -1, you can say that vectors are opposite, right? Opposite to each other. So means two data set which we are trying to do the comparison. So obviously it is going to be opposite to each other. Now angle wise, as we know, so cos theta, is nothing but a dot b divided by a length of vector a into length of vector b, right? So here, if angle is 0, angle wise I'm trying to explain. So if theta is equals to 0 degree, so in that case 1. If it is theta is equals to 90 degree, so in that case value is equal to 0. And if theta is going to be 180 degree. In that case, it is going to be -1. Simple, right? It is going to be -1 over here. Now, so you may get some sort of a result in between 1 and -1. Every time you will be able to get a result between 1 and -1. Now for our example, the example that we have taken, so what is going to be the result? How we are going to find out the cosine similarity? Let's try to understand. So first of all, what we will do? So we will try to find out a cosine similarity between this query and a data from ID1. Then query ID2 and then query ID3. So that we will try to understand that which one is similar, which one is more similar to the query vector that we have, right? So this is where cosine similarity we are going to use, and this is the calculation we are going to do. A very simple calculation. So like a dot product divided by length of vector A into length of vector B. So now let's try to do the math over here. Math for what? So math for ID1 data, right? Math for ID1 data. So what is the ID1 data, by the way? So ID1 data is 1, 2 versus a query. So what is my query? So query is basically 2, 2. So in between these two, I can try to find out the cosine similarity first, right? We can try to check that whether these two are similar or not. Now to find out a cosine similarity, right, between these two. So let's suppose we have a Q over here, we have a ID1. So we have to find out, I'm assuming that this is A and this is B. So here we have to find out A and we have to find out a B. B is nothing but my query, right? So here B for this one is going to be 2 square plus 2 square is equals to root of 8 is equals to 2.8284. So this is going to be this one. This is going to be for B. Simple, right? For A, so again 1 of a square plus 2 of a square, right? So basically we are trying to find out the magnitude. So 1 of a square and 2 of a square. Now what is going to be the like a 1 square and 2 of a square? So it is going to be root of 5, which is eventually going to be 2.2361. Okay. So we are able to find out this one. Now let's try to find out the cosine similarity. So cosine similarity is nothing but cosine similarity between vector A and B is nothing but a dot product of A and B divided by magnitude of A and into magnitude of B. So this is something called as cosine similarity, right? Now what is the dot product of A and B? Because denominator we are able to find out anyhow. So we can try to put up this denominator, but what is the numerator, by the way? So numerator dot product is nothing but, right? So dot product between 1 and this one. So basically A and B, dot product between A and B is something that we are supposed to find out. So how we can try to find out a dot product in a very first place for this kind of a data, for this ID like 1, 2 and query is equals to basically 2, 2. Let's try to understand that part. So let me write down that dot product, and many of you may be like aware about it. Maybe many of you are not aware about it. So let's suppose we have a vector A and a vector B, right? And a vector A, let me write it down somewhere here formula wise. So let's suppose we have a vector A. Vector A is nothing but A1 and then A2. Yeah, A1 and A2. And we have a vector B, and vector B value is B1, and let's suppose we have a B2. Yeah. So a dot product of A and B is nothing but, very simple, right? Very simple. So dot product is nothing but A1 into B1 plus A2 into B2. That's it. Yeah, that's it. This is going to be the dot product. Okay, so here we have a vector. So what is going to be the dot product? Let me write it down. So 1 into 2, 1 into 2 plus 2 into 2 divided by what? So divided by magnitude of A, 2.2361 into magnitude of B, so 2.8284. Okay, so if I'm going to do the math, right? If I'm going to do a math over here, I will be able to find out a final value, right? I will be able to find out a final value is equals to 0.949. Now this is the value I will be able to find out between ID1 and query. Yeah. So this is the cosine value between ID1 and basically a query vector. The value is what? Value is 0.949. Okay. So 1 is done. Fine. Now then ID2 and query. So what is a distance cosine similarity between ID2 and a query? So again, similarly, we can try to find out the way we are able to find out this one. So we can try to find out even for ID2 and a query. So that is going to be, cosine similarity is going to be 0.980. So for a second case, then ID3 and a query. So what is the cosine in between? So ID3 and ID not 3, ID4, right? So ID4. So we had basically ID1, 2 and 4, 3, 2. So what is a similarity between these two, or what is the cosine similarity between these two? So ID like 4 and query. So ID4 and query cosine similarity is again going to be 0.980. Yeah. So for third one. So we had 3 data, and for all of these 3 data, we are able to find out the cosine similarity. Yeah, we are able to find out the cosine similarity. A very simple thing, right? We are able to find out the cosine similarity. So here, right? So here we can try to prepare a chart, ID and then cosine. So this chart wise, ID1 and then cosine is basically 0.949, ID2 0.980, and for ID3, so we have ID4 we have 0.980. And let's suppose ID3 is not available in this cluster, ID3 is available in some other cluster. So even for ID3, we can try to find out basically a cosine similarity. That's also possible. Yeah, that's also possible for me. So maybe for ID3, it's possible to find out the cosine similarity, but let's suppose I'm not finding it. It's completely fine. Leave it for now. Now, if someone is going to ask you a question, right? If someone is going to ask you a question that give me a top 2 result. Yeah, give me a top 2 similar vector. So which vector is going to be a top 2 similar vector? Yeah. So what will be your answer over here? So here cosine similarity is this, this and this, at least for 3 vector 1, vector 2 and vector 4. When we are doing a comparison, so we have a cosine is equals to 0.949, 0.980, 0.980. So which 2 or which one is having less distance by the way? Yeah, so less distance by the way. So which one is having a less distance? So here, right? So here we can say that top 2 vector, which is very much near, right, which is very much near to my query vector, is ID2 and ID4, 0.980, 0.980, right? These are the top 2, right? These are the top 2. And again, so if you will look closely into the data, right? If you will look closely into the data, so here we have a query 2, 2. So 2 and 4. So 2, 3, 3, 2. So 1, 2 is not that near. It's little bit far, little bit, right? Not much. But yeah, 2, 3 and 3, 2 is nearest one with respect to this query vector. And this is the conclusion that we are able to find out. This is the conclusion that we were looking for with the help of cosine similarity. So cosine is always going to give you basically what? So cosine always try to give you the similarity search result. And here we are able to find out that ID2 and ID4 is the nearest one. Yeah, ID2 and ID4 is basically a nearest one. So my final answer, so in terms of top 2 search or top K search, we say, right? So we have ID2 and ID4 nearest one for my given query. Yeah. So top 2 result is going to be value which is available at ID2 and value which is available at ID4, as its distance is minimum 1, right? Minimum 1. And again, so you can try to find out a cos theta with respect to this particular value, which is available in a radian. And you will be able to even see values. So this is how, right? This is how we always try to find out a similarity. Again, I can try to use a Euclidean distance as well for like doing the same operation. But yes, cosine is a widely used things. Plus, one more thing I would like to like explain once again, that here we are not doing comparison with the ID number 3, because ID number 3 belongs to another cluster. So we are trying to even avoid lot of computation over here, lot of calculation, because as my data set is going to grow, obviously I will be having n number of clusters, and with all the data I should not do the comparison. So here we had in total 4 data, but we are doing comparison with how many data? Only with 3 data, right? Only with 3 data. We are not even considering the fourth one, because the reason is very simple. That data set is far away, or that data set is available into a different cluster. So that is the advantage of the indexing. That is something called as indexing of the data. So whenever we try to store the data, system is going to call the indexing. So for example, IVF indexing system is going to call, and the system is going to store a data into a different vector space. We say like IVF, right? So IVF is one of the way to do a indexing. So inverted file indexes, or inverted file we try to create, where we try to store a different chunk of the data. And then when someone is going to fire a query, we never look into all the data. So we just look into a data where the centroid of the cluster is near to the given query, and that is going to do the calculation, that is going to give you the final result. So hope this entire vector concept and how vector calculation happens internally is clear to all of us. Like I said, so cosine similarity and IVF. So IVF for indexing I talked about, and then cosine similarity for a similarity search I talked about. Now this is not the only combination. Likewise, there are many more other combinations which exist in terms of doing a indexing and in terms of doing a similarity search. And plus, many people gets confused between the indexing and the similarity search. Never get confused between indexing and the similarity search. It's very simple. Indexing means we are trying to divide a data into a different chunks or the clusters. Similarity search means, so inside a particular cluster, we are trying to do the mapping, so that I will be able to get a top n number of result, or we say top k result I will be able to get out of it. So with that, thank you so much everyone. Take care and see you again in my next lecture, guys.